Every single second, billions of connected devices are firing off massive amounts of data across the globe. To keep traffic organized, every internet-connected device needs an IP address. It functions exactly like a street address. This legacy format uses two parts. The network ID guides data to your neighborhood, while the host ID pinpoints your specific door. The original internet architecture uses a 32-bit system. Mathematically, that put a hard cap on the total number of unique addresses at roughly 4.3 billion. In the 1980s, 4.3 billion seemed inexhaustible. But as modern smartphones and sleek smartwatches and smart TVs joined the network, we completely reached the limit of these raw addresses. The math that built the early internet cannot support the current volume of devices. This scarcity created a massive structural bottleneck. We must completely change how we identify hardware. Since we have already reached that address limit, you might be wondering why your home devices are still able to connect to the internet today. The internet relies on a workaround called network address translation. Your ISP assigns one public IPv4 address to your home router. The router uses that single IP to hide your local devices from the public web, assigning them generic placeholders. This keeps you connected, but it forces your router to translate the incoming and outgoing traffic for every single device. This creates a processing overhead that slows down your local hardware. NAT was designed as a temporary fix. It actively breaks the direct end-to-end connection the internet was built for and masks the need for a permanent architectural upgrade. To resolve this address shortage permanently, the engineering community developed ipv6, an architecture designed to accommodate the massive growth of connected devices. Comparing the structures, IPv4 uses a 32-bit space, while IPv6 jumps to a 128-bit space. IPv6 uses alphanumeric hexadecimal digits grouped by colons instead of decimals. This expands total addresses from 4.3 billion to 340 undecillion, that is 340 followed by 36 zeros. This provides enough capacity to assign a unique IP address to every single atom on the surface of the Earth with plenty left over. This scale allows every device to have its own public internet address, removing the need for NAT and router bottlenecks. We lose human-readable simplicity, gaining a direct, one-to-one addressing system that scales with the global network. Beyond address size, we must examine the shape of the data itself, specifically the packet header, the shipping label for digital information. As this diagram illustrates, despite longer addresses, the IPv6 packet design is simpler. It uses a streamlined, fixed-size base header, removing complex, outdated fields like header checksum and fragmentation, leaving a lean layout. Standardizing the header size allows core internet routers to process and forward packets with less computational effort than the legacy format required. Implementing this requires replacing or upgrading legacy routing hardware to ensure it can parse this streamlined packet design. By reducing the data overhead in every packet header, IPv6 is able to minimize the processing time required for high-volume backbone traffic. Security is also integrated into the protocol itself. IPv6 makes IPsec, or Internet Protocol Security, a mandatory requirement. This means data encryption and device authentication are built into the foundation of the network, rather than being added on. There is a common misconception that IPv6 relies only on manual static routing. In practice, this is not the case. IPv6 uses UG3 versions of standard dynamic routing protocols, such as OSPF-v3, to map out the network automatically. The massive address space works with these native security mandates and dynamic protocols to create a modernized network architecture. The main challenge with this upgrade is that IPv4 and IPv6 are incompatible. They cannot talk directly to each other without assistance. To manage the transition, most networks utilize a method called dual stacking. In a dual stack configuration, your operating system and network equipment run both protocols side by side, processing both types of traffic at the same time. For IT departments, this temporarily increases the workload, as they must configure, troubleshoot, and secure two different systems simultaneously. Until the world fully moves away from the legacy protocol, administrators must maintain these two overlapping network layers. Here is how you should handle this transition based on your specific goals and network role. For IT students, mastering IPv6 structures and hexadecimal subnetting is no longer optional. This is the industry standard for modern networking certifications. If you are a home user, keep ipv6 and dual stack enabled on your router. This future-proofs your home network and removes the limitations of NAT. For enterprise admins, the configuration load is heavy, but planning migration now is necessary to gain the faster routing and security of the new protocol. The transition requires temporary effort, but leaving the limited ipv4 system is the only way to build a natively secure network growing with global demand.